And I'd like to hand over to Vladimir to kick off his session. Vladimir, I think you're on mute. So if you could unmute yourself.
Yes, sorry. Could you hear me?
Now we can, yeah.
Okay, great. A couple of seconds here. I will enable the sharing.
We can see your screen.
So do you see my screen now?
Yep.
Okay, good. So let's start. The topic of our last talk for today would be how you could easily speed up your deep learning inference. So the solution here would be write once, deploy anywhere. I'm a software solutions engineer at Intel. So let's begin. This is a system configuration that were used for the testing for our benchmarks. So let me start from how AI is changing industries nowadays. So nowadays, AI have been used in many spheres and industries. There are many examples of really breakthrough AI usage. For example, a couple of weeks ago, DeepMind released their study how AlphaZero, trained for discovered faster matrix multiplication, could be used for that matrix multiplication, and they found better algorithms than the state-of-the-art solutions. So now modular architectures and performance hardware solutions become an integral part of the progress. The complex tasks now could be easily done by the artificial intelligence, and it's enabling new and enhanced use cases in various industries, from, for example, something industrial to health and life sciences to retail to safety and security. But there is a question, are the requirements for AI-based solutions the same for all of that industries, and how it could be changed, how it changed from the previous years to now? Let's have a look at this graph, and it's showing total addressable market for artificial intelligence inference by different chipsets. In addition to the general increase in use for the inference devices, there will be an increase of use for the edge inference devices like ASIC, so application-specific integrated circuit, and also FPGA devices. A couple of years ago, the market for such devices was practically empty, and all of the inference was done on CPU and GPU. And as far as I remember from my experience, for example, in 2017, most of the projects were the inference were done by the GPU. So even at that time, it was really hard to port your deploy on the CPU. So edge devices are pieces of equipment that serve to transmit data or workloads between the local network and the cloud. And AI processing of edge devices have some privacy concerns while avoiding the bandwidth, latency, and cost concerns of cloud computing. Okay, I think it's clear here. So let's go to the next slide. The worlds of the neural networks, world of the deep learning and artificial intelligence could be divided into two parts. First part is training, and second part is inference. So training, it requires more mathematics. It requires the ability to analyze some parameters, some hyperparameters from the start, from the experiments. The normal behavior here is to have some experimental board and other monitoring tools, and it's more easy to integrate new layers. It's more easy to modify your layers, your architecture. And most of the workload here for the training, it's done on the GPUs. And for example, when you would try to port that workload for the inference to some other device, you could easily observe that the requirements for that device are different, or you even can compile some library that you have dependency on. So for inference, you could discard, for example, 80 or 19% of the mathematics. So you don't need to calculate your gradient. You don't need to have a backward pass here. It's faster than the training, and it requires a lot of less specific calculations. So you better to use a different device for that, because using a GPU here for some real-time workload, it's not really it's not really cost safe. So inference could be done on desktops, it could be done on mobile devices, it could be done on servers, and even you could infer some neural networks in browsers. And OpenVINA focuses on deep learning inference, not on the training. So even with the amount of breakthroughs I said before and new opportunities, deep learning enables still much challenges today. So first challenge is unique inference needs, and deploying your workload, the deep learning workload from training environment. So training environment is typically some data center or cloud to some real world production. It's a very challenging case because there is significant gap in performance and accuracy seen in trained models compared to what could be deployed in the field. For example, if you could find a graph for some topologies for some architectures, for example, the SIG-former, which is a semantic segmentation model, you could see that only first of backbones, which has less parameters than the others, could be deployed in real time on the not on the GPU, let me say. And it's really hard to have some balance here between the accuracy of your model and between the amount of parameters it has and about the inference time. Second one is integration challenges. So typically the training of deep learning networks is performed in data centers. And when you need to transfer that workload from the cloud to the inference device, there is some disconnect here in end-to-end development workflow. So another libraries need to do the inference, for example, or another library needs to have some optimizations. So from the software perspective, there are various languages. For example, if it's ASIC, it could be easily done on the C++, but your trained network would be on Python or on PyTorch, for example. And also it could be some dependencies here. For example, if you want to launch your network on ARM device, there could be, you wouldn't found some of the libraries that are precompiled for the other architectures. And the last item here is no one size fits all. So there are very different and diverse requirements for the corner use cases, corner cases that requires the unique approaches. And for every problem that could be a unique combination of networks, of models and target devices. So here, it's hard to find a unique solution for all of the problems that would fit all of that problems. Let's have a look at AI inference target devices. So hardware in artificial intelligence computation could be very different, and there are several directions of the inference. First one is the server inference. It's scalable, it's fast, and when you need to work on the high performance server, you let me say, rarely need to deploy that workload to the specific device, like a mobile phone, like maybe a browser, like ASIC. So here is the server inference mainly used when you have much data, much workload, or you need to process that workload really fast. Second one is a desktop inference. It's something that could be run on your, for example, home computer. It's photos processing, it's video analysis. It's also the computers that could be an enterprise, for example. So it could has both CPU and GPU. So in that case, it would be really hard if you have some workloads. You need to check the amount of memory that it takes. For example, if you would you will take much time, much space on your GPU. It could be lead, for example, to low productivity in the games. For example, if you're doing the inference of some camera software. Next one is mobile inference, and next one is the embedded or edge inference. So it's not really scalable and not really fast. And talking about the determinants of such configuration selection for the edge, more matters power consumption, the price, the size, location. So location would be availability and quality of internet channel. For example, if you have a very low bandwidth on some edge device, you cannot transfer that workload. For example, if it's video stream, it would be really hard to transfer that workload to the server. So you need to have an edge device to infer that workload. And also the location conditions, for example, the temperature, the dust and moisture protection. Let's go to the next slide. So the Intel distribution of OpenVINA toolkit, it's a tool suite for high performance deep learning targeted as faster, more accurate real-world results deployed into production across Intel architectures, starting from edge and to the cloud. It enables high-performing applications and algorithms to be deployed in the real world. And in addition to that, it simplifies the streamlined workflow for the development. So with write once, deploy anywhere approach, developers could write an application once and deploy it across different Intel hardware. Like including the CPU, including integrated GPUs, including VPU, and also GNA. And the operating system for that devices could be different. And for the new release, which is 2022.2, also the Digi2, the new Intel Arc support will be added, so added already. On that slide, you could see how the compounding effect on both hardware and software improvements could improve the model performance. So here the exponential performance could be realized. Intel is continuously shipping new hardware with built-in agility to adopt AI and deep learning with scale and flexibility. So for example, when you will, let's take first generation of Xeon processors. For example, when the second generation of Xeon processors were released, and the Intel Deep Learning Boost, which has the VNNI instructions enabled, so we could see the 4x faster performance. With new major version of OpenVINA, it would be 5 times faster than the baseline. With new release of the Xeons, it would be 10 times faster. And with the newest major release of OpenVINA, also more 3x times faster, so 13 times faster than the baseline. Another compounding effect of hardware and software is multiple device usage for the inference. For example, here we could see usage of both devices, so integrated GPU plus CPU compared to inference on only one device. So first one is on the CPU inference. Second column is the integrated GPU inference. And third column is multiple device inference for some of the well-known architectures here. So on that slide, you could see the summarized view of the streamlined development workflow of the OpenVINA toolkit with 3 sections. So first one, you could build a model with deep learning framework that you want. Second one, you could optimize this model with model optimizer or deep learning workbench. And third one, you could run that inference on the selected Intel hardware with Inference Engine API. So let's look at the steps closer. First one, if you want to have a pre-trained model, you could take it from many popular frameworks nowadays. So it's a TensorFlow, it could be PyTorch with import to NNX, it could be even Kaldi. So Kaldi nowadays still used for some ASR tasks, so speech recognition, and also working with some language models. MXNet, Caffe, and also Pedal. So, but also you could take some pre-trained models from OpenModelZoo. So OpenModelZoo is the model repository for OpenVINA toolkit, where you could find more than 300 models in different data types. So it could be FP32, it could be FP16, and even it could be the int8. Yes, I already said you could find many models, and it would be related to a different task, different problems, but that's all we had. Next step would be a model optimization. So OpenVINA toolkit have a tool called Model Optimizer. It's a tool that converts the original model in some deep learning framework format to the intermediate representation format. So intermediate representation format is the OpenVINA toolkit format, which would be 2 files here. So first one is a binary file. It would describe the weights and biases of the data. And second one would be the .xml file, which would describe the network topology. So the topology and the format for the model in OpenVINA toolkit is also a computational graph, like in ONNX, for example. It's also talking about optimization techniques that are available. First one is linear operation fusing. Second one is straight optimization. And third one is group convolutions fusing. So let's review one of the optimizations here. So during training, batch norm layers, for example, it's needed. It sees the whole batch. It sees the mean, it sees the variance, and it's learning that parameters. For example, in test time, we don't need that layer. That layer should only see the test data, one test data at a time point. So we don't need it during the inference. And we're removing the batch normalization here. We recalculating the weights for the other operation to include that parameter, that weights, and we merge convolution and real activation into one optimized kernel. So that's how the optimization for that type of optimization could be done. Post-training optimization tool. So you could find different conversion techniques that Nikolai already just talked about. For example, it could be quantization. So for OpenVINA, you could do simply quantization for the static algorithm, so static quantization, and you also could do dynamic quantization, which would calculate the accuracy connected to the precision type of the layer, and it would do automix precision to calculate the most usable types for all of the layers. So it would lead to most to the highest accuracy here. Deep Learning Workbench. So it's a web-based UI that could be used for model analysis and also some graphical measurements, graphical visualization. So you could visualize performance data for the topologies and also layers. And that would help in the model analysis. You could automate analysis for the optimal performance configuration, for example, streams, so amount of streams, batches, or also latency. You could experiment with int8 calibration or use the post-training optimization tool to select the best configuration. And all of that could be easily done with within the browser window. So it's our web-based UI tool. And finally, you need to deploy your workload. So inference engine runtime, it's written on high-level C and C++, and it also has the Python inference API. It's implemented with dynamically loaded plugins for each hardware type. For example, for CPU, it would load one plugin. For the integrated GPU, it would load another plugin. But the conversion, it could be done on all devices, and it would just have the same result. So let's have a look at that graph. So you could run, you could just write once and deploy your workload across different platforms. So it could be CPU, it could be GPU, it could be also server CPUs, it could be some edge devices, it could be neural compute stick, which also have some Mavideos cores in there. Let's review that inference engine architecture diagram. So there are two categories of libraries for that inference engine API. First one would be the core libraries, and second one would be the device-specific plugin libraries. So the core libraries that are used for the creating of the inference engine core object to work with all of the devices, to read that network, which would be in the intermediate representation files. And also you could, for example, reshape the input. You could load that network to the selected device, but next operations, next inference would be done by that plugin. So when the network loaded to the selected device, each device-specific plugin library performed its own optimization. It would be the device-specific optimizations to the network passed to the runtime. Talking about additional tools which we have in OpenVINA toolkit, it could be good to have for example, the OpenVINA model server. It would be the orchestration tool. So you could load many models to your devices and have some optimized inference with REST API endpoints. And also deep learning streamer, it could help when you have multiple streams of the video. So you could decode, for example, Z streams in real time and have some AI inference, for example, the object detection models there, or semantic segmentation models right after that decode function. So computer vision annotation tool, it could help to annotate images before training a model. And so if you need some additional tools here, you could also find it in the OpenVINA model repository, OpenVINA toolkit repository. What's new in our major release So first one is updated API. Second one, we support more models, for example, the NLP models, and also some anomaly detection, and also paddle framework, and also new auto plugin could be used to run inference workloads dynamically across multiple devices. So for example, you could run different layers on the different devices. That is more that would be better supports that layer, for example. So you could divide your workload between the CPU and between the GPU. So first one, you would compile that network for the CPU. Then you will start your inference on the CPU, and when the network would be loaded to the GPU, you would have that CPU inference, and then the GPU inference will start. So you don't need to spend time here on waiting when that model would be transferred to the integrated GPU. Also, new feature is dynamic input shapes for the CPU. So if your task is NLP, where input size varies from sample to sample, the solution here would be the dynamic shape, and it would automatically resize the network based on the given input. So you don't need to do it by yourself. When we are talking about the edge intelligence solution, so it consists of the inference device, the algorithm, that or your workload, and also some business application. So, for example, the device that you could take for the edge inference, it's our Tiger Lake Nukes. So it have both CPU and integrated GPU, and you could transfer the workload between the two devices. And also the new Insolaris graphics, it's could be used for the inference of most of the computer vision architectures that also have some Intel deep learning boost instructions, and also it could be used for the decoding of the input video streams, and it's not supporting only one stream, but it could be support much more video streams. Again, the combination of CPU and GPU inference gives you many possibilities. For example, it would be the GPU video stream decoding. It also could be CPU or GPU offload for the different device. For example, if you have a specific network that you want to run on the CPU, but it's already you have some workload there, you could port your second workload to the GPU and infer the unique workload on the CPU, so it could be offloaded on the different device. Third one, it could be used for separation for different models architecture, and also you could infer your workload in multi-device mode. So you could find many demos in OpenVINA Toolkit model in OpenVINA Toolkit repository on GitHub. So many use cases for the real workloads, for example, the parking counters, some store traffic monitors, and many more. But my support would be, but my suggestion here would be the OpenVINA Notebooks repository, which also could be found in OpenVINA Toolkit's basic repository. So it contains many notebooks with which you could run step by step to optimize some models to see the performance improvements. And also it has some real-time demos that could be run with your laptop webcam, for example. So if you're ready to get started, just download the OpenVINA Toolkit free from Intel website, and now it could be downloaded from the pip. So pip install OpenVINA and pip install OpenVINA/dev. So from just OpenVINA package, you will receive the inference engine, and from dev, you will receive tools like model optimizer. And let's have a look at demo. If you could see the screen with Jupyter, please, someone reply.
We see it.
Okay, great. Thank you. So let's have a look how we could convert a PyTorch model first to NNX, and then second to the OpenVINA intermediate representation. So I will done it in real time. First section is an import. Second section would be the settings. So here we would have a FastSeg model with limited image height. So let's, I have it already, I think. And let's convert it to the ONNX. So using ONNX export function. Okay, it's now exported to that location. So that ONNX model could be converted to OpenVINA intermediate representation format. And for example, during that conversion, you could specify different parameters. For that model, it would be the shape because it's limited for the such shape. It would be mean values and scale values that are used for the image pre-processing. And let's run that command. So for that model configuration, it's the model optimizer tool generated both files, XML and bin. It takes not so much time. So let's have a look on the inference results. And we will inference, our inference workload would be an image, just a sample image. So let's resize and normalize it for the ONNX and Torch. And let's, first of all, let's try to load the ONNX model directly to the OpenVINA runtime. So OpenVINA could also work directly with the ONNX models. And you could see the output here for the ONNX model. And let's test if it's similar to the OpenVINA. It's pretty similar. So we also could compare it with the stock PyTorch. So that PyTorch model that we just downloaded from the model repository when we don't apply any conversion techniques, any conversions. So the output is pretty similar, but let's have a look at the performance. So we will infer it on the 20 images and just compare that numbers. So let's wait a couple of seconds. And also let's have a look at the device information. So I infer that models on the third generation Intel Xeon Gold. You can see the model on the screen. So let's have a look at the results. PyTorch model on CPU, it's 1.5 seconds per one image. And for ONNX model that we run with the OpenVINA toolkit, and OpenVINA intermediate representation model. It's pretty similar performance. So it's 26 FPS versus 0.65 FPS with stock PyTorch. So pretty good results here, I think. And after that conversion, that OpenVINA intermediate representation model could be easily deployed on the other devices, like integrated GPU, like VPU, MyVideo's VPU. The one thing you need to change for that would be specify the device name. And all of that optimizations for the specific device would be done automatically for that, for VPU, for example. So if we have some time, I think we have some time, let's review how we could load the network and infer that with OpenVINA toolkit. First one, you need to create the inference engine object here. Next, you need to read the model from your path. And you need to compile model for the specific device. For example, in our case, it's the CPU. And you will get the input and output layer. Because it's the computational graph, you need to specify the graph node, which output you will take as an output. So then we just see the output, we do the inference for that output layer. So nothing special here, I believe. The same behavior, the same inference steps you could observe in any other frameworks, like in ONNX, which is also an inference framework, and in PyTorch, it's not really different from the PyTorch, for example. Okay, I think that's all from my side today. If we have any questions for the presentation, for the demo, just ask me. And thank you for the listening. So I will monitor a chat if we have some questions. I don't think we have any questions in chat, so just we'll wait a couple more seconds for the questions.